Hello and welcome everyone. Thank you for joining us today for our webinar titled Responsible Machine Learning with H2O Driverless AI. My name is Patrick Moran and I'm on the marketing team here at H2O.ai. I'd love to start off by introducing our speaker. Navdeep Gill is a senior data scientist software engineer at H2O.ai, where he focuses mainly on machine learning interpretability and previously focused on GPU accelerated machine learning, automated machine learning, and the core H2O3 platform. Prior to joining H2O.ai, Navdeep worked at Cisco, focusing on data science and software development. Before that, Navdeep was a researcher/analyst in several neuroscience labs at the following institutions: CSU East Bay, UC San Francisco, and the Smith Kettlewell Eye Research Institute. Navdeep graduated from CSU East Bay with an MS in computational statistics and a BS in statistics and a BA in psychology. Before I hand it over to Navdeep, I'd like to go over the following housekeeping items. Please feel free to send us your questions throughout the session via the questions tab. We'll be happy to answer them towards the end of the webinar. And this webinar is being recorded. A copy of the webinar recording and slide deck will be made available after the presentation is over. And without further ado, take it away, Navdeep.
Thank you, Patrick. So like Patrick mentioned, the title of the talk is Responsible Machine Learning with H2O Driverless AI. So before we begin, I'd like to give some background about this presentation and what we'll be talking about. So transparency, accountability, and trustworthiness, are a big part of a lot of regulated industries today, whether it be banking, insurance, healthcare, and other industries. A lot of this should also be accounted for in other industries as well, like IoT, or if you work at a startup or anything like that, because if you can't really trust your machine learning models, then you can't really deploy them out into the real world. So being responsible in this aspect is very important for a lot of data scientists. So the problem statement we're trying to figure out today is, can the productivity and accuracy advantages of automated machine learning, can they be leveraged in highly regulated spaces? I would like to mention that we at H2O cannot really provide compliance advice in this manner, but we like to think that these tools can be used in a very responsible manner, and you can get a lot of output from these types of tools. Now, when I talk about AutoML, I'm specifically talking about H2O Driverless AI, which is a system that does auto visualization, automatic feature engineering, trains models, explains models with minimal user input. So the idea here is this tool can be used to work on many use cases for your business, and you can work on them in a more productive manner, without having to worry about model tuning or manual feature engineering. A lot of this stuff can be automated for you with Driverless AI. So with that background information, I'd like to go over the agenda that we'll be focusing on today. So I'll be going over these 4 things. So, an intro about, explainability and responsible machine learning, why this concept matters, what you can do as a user to have more of a human-centered, responsible machine learning approach with Driverless AI, and how you can explain models with Driverless AI. So here's the intro. So first off, we would have to go over some terminology that will be used throughout the presentation. So the first term is machine learning interpretability. So it's the ability to explain or present in understandable terms to a human. So by machine learning interpretability, you should be able to take an output of a model and explain it to business users, analysts, stakeholders, and explain to them why a certain decision was made. This is highly important for regulated industries, but it should also be accounted for in other industries as well, as you need to establish a level of trust and understanding with the machine learning model that you're deploying. Now, AutoML will be referenced throughout this presentation. By this, I specifically mean H2O Driverless AI. So I mentioned earlier that this is a AutoML type of tool, which automates a lot of processes in the data science workflow. So as I mentioned AutoML, I'm referring to H2O Driverless AI. And of course, I'll reference something called the MLI module, or MLI in this case. And by this, I mean MLI module in H2O Driverless AI. So Driverless AI has a component that does machine learning interpretability. So when I reference MLI, I am referring to this component. So now we will go over a sort of the type of pipeline someone goes through in their machine learning endeavors. It starts off with data integration and quality. Once you have your data set prepped and ready, you've cleaned it up, dealt with missing values, dealt with duplicate rows, anything like that you would typically do. Then you move on to feature engineering, model training, and before you deploy the model, you would kind of want to interpret the model to see what it's doing. So here are some terms that here are some applications we have in Driverless AI that I'll go over later on. So, from MLI, you would do things like disparate impact testing. So this has to do with making sure that different groups of people or observations are treated fairly with the model. You can do what-if or sensitivity analysis with Driverless AI. So this has to do with model debugging, seeing what happens when you change certain inputs to the model and how the output changes. You can look with Driverless AI. You can look at things like feature importance. You can get reason codes, which is from Shapley and Lime. You can use surrogate models to figure out how the model is behaving itself with maybe a more simpler model. You could look at things like partial dependence and ICE, which have to do with how the model's output changes as you change certain inputs. And of course, the final step of this is sort of model documentation, which most people are probably familiar with, especially if you're in banking or in insurance or healthcare. You sort of have to document what the model did, what sort of inputs it used, the distribution of the training data set versus the validation and the test. So this is what we call AutoDoc in Driverless AI. This is available to all users as well. Now, as in this pipeline itself, you could imagine that the feature engineering and the model training could be highly complex, and this might make the MLI aspect a little more complicated to use. And of course, the MLI aspect does not have to always be at the end. You can actually, with Driverless AI, you can have MLI as the entire pipeline. So having interpretability in mind throughout the entire pipeline. You can constrain certain interactions with the feature engineering, and you can build interpretable models. So this is things like monotonic BBMs or generalized linear models. All of this can be limited in the scope of Driverless AI to avoid highly complex models if that is what you are concerned with getting. So you can, like I mentioned before, you can build, a very accurate model and then interpret that accurate model and try to get some insight, or you can have interpretability in mind throughout the entire process. This is available in Driverless AI. This is something you can do today. So the next topic is, why does responsible machine learning matter? So the first thing to keep in mind is sometimes there is a potential trade-off between performance and interpretability. So we have, we can have white box models, which are models that are highly interpretable, and you can have black box models, which are very complex. So think of like a simple decision tree versus a very complicated neural network. When I say the potential trade-off, I mean there might be potential trade-off between accuracy. Work has been done lately that shows that you can get very highly accurate models that are also interpretable, but sometimes, there still is this trade-off that can happen between the two. Also, when you have explainable models or models that are highly interpretable, you can get exact explanations for approximate models. And if you have very complicated models, you can get approximate explanations for exact models. So imagine if I build a very complicated neural network, I can get approximate explanations for that complicated neural network using things like Lime. However, I can also get exact explanations for that model by using something like Shapley, for example. Another thing to consider with responsible machine learning is this concept of multiplicity of good models. So, for a well-understood data set, there might usually be one best linear model. However, there might be many good machine learning models that are not linearly based, like GBMs or neural networks. So, which one do you actually choose? The concept itself is from Leland Williamson. For a given data set, you can have many models that work, and you yourself as user have to figure out which model to use and use certain objectives to figure that out. One objective you can use is sort of which model is more fair. So you can build several highly complex models and pick a model that is the most fair to your training data set, or the most fair to observations seen in your training data set. Now, fairness and social aspects are very important, especially in regulated industries. You don't want a machine learning model that is biased based on gender, age, ethnicity, health, or sexual orientation. You want to make sure that everyone's treated equally for the groups that you're interested in. Another reason responsible machine learning matters is you sort of want to have trust of the model producers and the consumers. So, you might want to think about, your data set versus the real world. You want to ensure that the data set you use to train the model can be well represented from the real world. And you also want to make sure that your machine learning model itself will not, go haywire in the real world if it sees something that's, it never saw during training. So you want to account for this during your training process. You want to have some type of introspection into your machine learning model. You want to understand how sensitive this machine learning model is before you deploy it, whether that be through diagnostics or model debugging, which I will go over in later slides. But, a lot of these things should not only be accounted for in regulated industries. They should be accounted for in probably every machine learning application before you actually go out and deploy something that's going to make automated decisions for you. Another thing with responsible ML to consider is the concept of security and hacking. So, sometimes a model can be deployed and it can be hacked. There have been studies that have shown this is possible if the model is available through a certain API. So someone can use, let's say, like a surrogate model, which will be trained on the predictions of your model and sort of figure out what the inputs were, and based off that, build out data sets that represent the training data set used for your model itself. You can avoid these type of things by using adversary data sets, or adversary instances. Try to figure out how you can, let's say, change the outcome of your model from being 1 to 0 or vice versa based off of some changes in your data set itself. You can look at the integrity of the model. So this has to do with false negative instances, fraud, path checking. You can also look at see your false positive instances. So a lot of these things can be explored before the model is deployed to sort of ensure that security and hacking are not a threat to you. Although another thing to consider with responsible ML is in many industries that use machine learning, they are also regulated themselves. So there's legal requirements about ensuring that you're using machine learning responsibly, whether it be banking, insurance, or healthcare. You sort of have to justify the decision that's made for an observation. This is usually through something called reason codes or adverse action notices. So adverse action notices are used in banking heavily, and it has to do with if someone is denied a loan or credit, you have to explain to them why they were denied a loan or credit line. So if you're able to do this adequately, then you're protecting your business and yourself from any adverse effects from deploying a machine learning model that does not make sense or people do not understand. So, in summary, the reason responsible machine learning matters, you want to have a balance between performance and interpretability. You want to think about the multiplicity of good models. So not only choose models based off accuracy or AUC or any type of metric, keep in mind about fairness and how interpretable the model is. You want to keep account of fairness and social aspects. You want to have some trust in your model itself. You want to keep track of security and hacking of your machine learning model. And of course, if you're in a regulated industry, you want to keep those regulations in mind. So now we'll talk about what's needed to build out this human-centered, responsible machine learning with driverless AI. So the first step with driverless AI or a lot of machine learning applications is, you want to load your data. So with driverless AI, you can load your data and you can instantly get some exploratory data analysis of the data set loaded. So this is sort of the first step in responsible machine learning, is ensuring that the data you have is cleaned up, it makes sense to you based off of your domain knowledge. It makes sense maybe to other team members that you work with, so they understand that the data used is representative of where this model will be deployed. So Driverless AI gives that to you out of the box as your data set is loaded in. Once your data set is loaded in, we have this concept of auto visualization. So this is work done by Leland Williamson, who's very well known for the grammar of graphics. And what this module does is, once the data set's loaded in, you can visualize the data set, and the auto visualization will figure out interesting characteristics about the data set and present that information to you. So this is really nice, because you don't have to do it manually, and you're taking the first step in responsible machine learning in an automated fashion, and you can iterate very quickly through these plots, figure out if there's anything that doesn't make sense, and if it doesn't make sense, you can sort of go on to the next step. So these are the type of plots you can get. It could be you can look at correlations, you can look at outliers. So these are the type of things that are a part of the pipeline with a human-centered approach. The next step is, sort of feature engineering. So like I mentioned before, in Driverless AI, we offer automated feature engineering. The features themselves can vary in complexity. So depending upon what your goal is, if your goal is to have an interpretable model, you can sort of play with this interpretability knob you can see highlighted here. In this case, where we turn the interpretability knob down to 1, which will produce a lot of features with varying complexity. So this is your goal, or if this is something you can deal with, then you can set interpretability to this level. However, if you wanted a sort of white box model or a white box type of feature engineering, you can turn interpretability all the way up to, say, 10, and this will make features that are highly interpretable. People can understand them. The explanations for these features make sense. So depending upon what your goal is, you can sort of go this route as well. From a responsible machine learning standpoint or an interpretable machine learning standpoint, you probably want interpretability to be, a little higher than 1, so you can avoid any misunderstandings with the features used. So here I have a few figures here that I'm showing in Driverless AI later on as well, but essentially what these two figures are showing is, on the top one there, figure 1, I am setting the reproducibility on for Driverless AI, so I can sort of get reproducible results, which is very important for machine learning. Also, I am setting the interpretability to 7, and what this does is this will give me feature engineering that's pretty interpretable for most people. These are features that you can present to business users or to analysts on your team that aren't probably advanced data scientists, but you can explain to them what this feature is, and they will understand it. Another thing setting this interpretability to 7 does is it adds monotonicity constraints. Basically, this basically means that as the input feature value increases, the output of the model can only increase, or vice versa. So this is something you can control with Driverless AI, something you can constrain the model itself to do. Another thing you can do is you can set which models to use and which models not to use in Driverless AI, which is shown in figure 2. So you can see there I've turned basically everything off except for XGBoost GBM. And since monotonicity constraints are on, this is a pretty accurate model that is modeling relationships in a monotonic way. So the inputs, outputs would make sense to someone, and this is something you can do before you even start your Driverless AI experiment. So once you've done, you've loaded data in, you've made sure that there's nothing funny going on, you've done some exploratory data analysis using the visualization module of Driverless AI, you've done feature engineering, and you've figured out what type of feature engineering you want, whether it be like white box type of feature engineering or black box type of feature engineering. Then the next step is to actually build out the models. Now, the type of model you want, depends upon what your end goal is. But if your end goal is interpretability, then you sort of want to build out these white box models, these models that make sense to people, these models that probably won't build out too many crazy interactions that are hard to comprehend. So you can do this just by, setting interpretability in Driverless AI to let's say like 10, accuracy 6, and the time is 4 here. So you can see I have monotonicity on again. I'm using tree-based models, and I'm using feature engineering like frequency encoding, one-hot encoding, looking for time variable. So these are features that people will very much understand, and these are features that are actually being produced by Driverless AI. So it's no work on your part. The system is taking over and building these out for you. So you can see here that this is sort of a breakdown of what the interpretability knob can do. So if you have interpretability set to 1 and 3, it will do a lot of feature engineering. It will build out ensembles. But you can see as I increase the interpretability up to 4, 5, 6 to 10, you see the ensemble level goes down, meaning my final model will be a single model or a small amount of models instead of a huge ensemble. The target transformations are sort of going away at that point, so the target remains in its normal space, and the feature engineering itself is getting a little more interpretable. And this is sort of going over some of the screenshots that you see in Driverless AI. So here, for example, I'm setting GLM and like DBM models to on. So just to go back over the models again, Driverless AI offers many interpretable models. We have GLMs, we have rule fit, and then I mentioned monotonicity earlier. So once that's enabled, all the tree-based models are essentially monotonic GMs. By default, Driverless AI will use an ensemble of several types of models, which can be undesirable for interpretability perspective. However, you can change this to say only to build no ensembles at all, which will probably play in your favor from a interpretability standpoint. So, for example, down here again, you can see that I have turned off all models except for the XGBoost GBM, and I've set the ensemble level to 1 here, which would mean only a single model will be built at the end instead of an ensemble of models. So this is going back again between balancing accuracy versus interpretability. If I built in a huge complicated ensemble, it might be really accurate compared to a single model. Maybe interpreting it will be quite difficult. So this is sort of a balancing act you can play with Driverless AI, and you can run many experiments this way and compare results, and then at the end pick the one that makes the most sense to you in your use case. Another thing we offer in Driverless AI is this mode called compliant mode. So what compliant mode means is it will force the interpretability knob to be 10. The types of models it will use will be GLM or rule fit. Treating of certain features like numeric features as categorical. It won't use any ensembles. The interactions are not too deep if it was for these type of models. The target transformer is pretty much turned off, and it won't use any distribution shift between train, value, and test to drop features. Essentially, this type of mode will do what I spoke about previously in one shot. So I can turn the compliant mode on, and it will set everything to these bullet points you see here instead of you having to do it one by one. Sorry about that. So yes, I was talking about compliant mode. So this is a way to sort of ensure that simple models are built, simple feature transformations are done in a sort of a one-click shot. So once the model is built, the next step in this type of pipeline is sort of assessment of the model itself. So looking at things like the ROC curve, lifts, gains, KS charts. All of these are built into Driverless AI. You can get these out of the box. This is not any manual work on your part. All of this information is available to you once the experiment is done. Another thing we offer, which I mentioned in the previous slides, is this concept of AutoDoc. So this is sort of a Word doc that goes over everything that was done in the experiment. So this is highly important in regulated industries, but it's also important in any industry that uses machine learning because you want to be able to explain to people what you did with your machine learning model and how you built it. So that this is nice in the sense that you don't have to do it yourself. It's done, automatically for you. So all this information is available to you at the end of the experiment, and you can distribute it to your team or to various stakeholders. And once again, in addition to the assessment that's done after the experiment, you can also run diagnostics of your model on a different data set. And then this is how you compare models on various test sets. So let's say you have model A and B, you can compare its performance on the test set, and you can get an output like this under the Diagnostics tab of Driverless AI. Once you've built the model, you've done the assessment, then you would move on to sort of this MLI component, which is, the what-if sensitivity analysis, reason codes, and disparate impact testing. And this is usually done by once the experiment is over, you can type in, or you can click on interpret this model, and then all of this stuff will be launched for you, and then the results will be available as well in the form of a dashboard in the MLI pane. And there's also other tabs that sort of go into each chart itself specifically. Once you've gotten to this point, the next step is this human review component, which is sort of making sure that the results you're seeing make sense to your use case. You sort of look at local instances of reason codes or adverse action notices, local instances of model debugging, global instances of feature importance, to look at the documentation, look at the performance of the model itself. This is where the human review comes in. But the beauty of Driverless AI is you can iterate very quickly, and you can jump to human review very quickly, and you can compare various models across diagnostics, across MLI, across accuracy and performance, and can tackle many use cases this way. So the next step is sort of how we go about explaining the output. If you recall, what Bill talked about responsible machine learning, a big component of that is figuring out what your model did and ensuring that you are not introducing any bias or any nonsense to the output itself. So this is sort of more of a deep dive into the MLI module. So once you're in Driverless AI and you click on interpret this model, you will get a dashboard like this amongst various other things. So I'll sort of do a deep dive into that. The main focus of this talk is I'll be focusing on IID data. So this is not like time series data or NLP type data, it's normal tabular data sets. That's the focus of these next few examples of these slides that I will be showing. So the Driverless AI module, it can sort of be broken down into this type of flow. We have sort of this global approximate model behavior interactions. This is usually done through this concept known as a surrogate model. We offer various kinds of these in the MLI module itself. You can look at global feature importance. So this is looking at things like Shapley values from a global manner, the model's feature importance, and then RF here stands for random forest, which is a surrogate model we build, and you can look at the feature importance of the surrogate model itself. We can look at global feature behavior, which is PDP or partial dependence plots. So on average, how does the output change if I change all the rows to a certain input? That's the concept of PDP. You can get reason codes as well. This is done through LIME, or we call it K-LIME, and I'll go over this concept later on. But essentially, this is building a linear surrogate model to the output of your Driverless AI model, and it's building reason codes, which are essentially coefficients of the GLM model, and then based off that, you can get global reason codes and local reason codes as well. I also put there, you can get a model's reason code. So Driverless AI offers Shapley values for a lot of models, a lot of tree-based models, and these are these aren't really approximate reason codes. These are the actual reason codes used by the Driverless AI model itself. And then, all of the stuff I just went over is done in a global scale. You can also do them in a local scale. By local, I mean looking at rows or groups of rows. This is all available in the MLI module today. So I'll go over, so later on I'll be showing a few experiments done in Driverless AI, and this is the data that we'll be using. It's a credit card data set, and The features itself that are used are things like limit balance, so the amount of credit given to a user. We have information about the gender, which won't be used in the model, but we have this information to check for disparate impact later on. We have the education levels, which won't be used in the model again, but we can check for disparate impact later on. We have their marital status, their age. We have their repayment statuses, and the amount they were billed and the amount they paid for the previous month. So this is data that will be sort of referenced later on in the experiments that I show, and I just wanted to go over now so people understand the type of features that you'll be looking at. And of course, I'll go over these features again as we're looking at the experiment. So the first thing you can look at in driverless AI is this global approximation to model behavior and interaction. So the challenge here is you have some black box model and you're trying to understand how it made certain decisions. One thing you can do is you can build a surrogate model for this. Now, what is a surrogate model? A surrogate model is maybe a more simpler model, like imagine a decision tree with a single tree that's built to the output of the complicated model. So this is building a decision tree to the y hat, or the prediction of the driverless AI model. And then based off that, you can plot that single tree and you can see how certain decisions were made. So you get this sort of model flow of what happened. So that's the pro to this type of approach. The con can be since it's a simple model, in this case it's a single decision tree, which is what we offer in MLI, the con can be the accuracy. The good thing is you sort of get a flow of what's going on, but keep in mind that if the accuracy is pretty low, then it's not capturing all the variance from those predictions. So this is a very good way, if it is pretty accurate, it's a very good way to kind of figure out what's going on with your complicated model from a visual depiction standpoint. So this is what I was just talking about earlier, how are surrogate models made. Here I built a model with my matrix of X features, my output Y, and the surrogate model is those same features but built to Y hat, which is the prediction of the previous model itself. So this is how you go about building a surrogate model. So based off this, you can see you can use a lot of things to build surrogate models. You can take a GLM and build a surrogate model for a complicated GBM, for example. Another thing we can look at is global feature importance. So this is the typical feature importance you would get from any machine learning model. You can look at this feature importance from a surrogate model as well. So in MLI, we build a reinforced surrogate model to the driverless AI predictions, and then we plot the feature importance of the original features used in that experiment. So based off this, you can sort of get some introspection into what the model thinks is important. So that's sort of the pro again, but the con is the accuracy. So you have to keep in mind if this surrogate model is accurate to your driverless AI model. We provide metrics in the MLI module to let you know how accurate it is, and based off those metrics, you can see if you trust the important plot itself. Another thing we offer is the feature importance of the original model itself. So you can look at the surrogate model feature importance and the original model feature importance, and you can compare and contrast the two to see how much a surrogate model is capturing from your model itself. This goes back to the whole security thing. If your surrogate model can capture a lot of variance in the output of your driverless AI predictions, the same can happen if, let's say, a hacker tried to get into your model itself. They can probably build a surrogate model to capture that variance as well. So it's something to keep in mind, and another application of surrogate models. And another thing we offer is Shapley Values. So Shapley Values, I'll explain in the next slide, but essentially this is a very robust way of getting feature importance. It's been tested a lot in literature. There's a whole package behind it. That's sort of the pro of this approach. The con is, it can take a long time to run Shapley Values, and we offer it for transform features currently, but we are working on a way to get Shapley Values for original features. So here's sort of a breakdown of Shapley Values, which I mentioned I will go over. So the inventor of this concept is Lord Shapley. He won a Nobel Prize for this work in 2012. So Shapley Values itself comes from game theory. Like I mentioned before, it's a highly complex calculation. So it has a lot of time complexity, exponential time complexity. So it's sort of unrealistic to compute in the real world. You can compute it on global scope, which is what I showed previously, but also you can take that same concept to local scope, which is for a row or a group of rows. The idea behind the Shapley value, in simple terms, is it comes from game theory, and the idea is there's a group of people playing a game, and there's some payout. And how can I equally distribute the payout amongst the people in the game, or how can I distribute the payout amongst the people in the game? That same concept can be applied to features, and the output is the prediction of the model. How are the features distributing amongst the outcome of the model itself? And that's where Shapley values come into play for machine learning. The traditional approach is highly complex, but there has been work done with Shapley values on tree-based models, which is what we use in Driverless AI, and that work has shown it can be done pretty quickly. And the time complexity sort of goes away, or almost goes away, with that approach. Another concept of feature importance that we offer is leave one covariate out. So the idea here is, with our random forest surrogate model, if I set one of the features to missing and then I rescore that model, how does the outcome change? And then that is sort of what we do with this concept of leave one covariate out. So this is another way of looking at feature importance. Assigned feature importance, just like Shapley plot itself. So you have various ways of looking at the importance of variables and comparing and contrasting how they're different with different approaches. So this is just sort of going over like sort of a matrix view of how this leave one covariate out would work. So we've gone over sort of the method so far, the random forest surrogate model, leave one covariate out, looking at feature importances of the original model, and Shapley value itself. The next concept is partial dependency. Concept here is looking at the average output of the model as you change the entire set of rows to a certain value. This sort of gives you the distribution of the predictions from a global scale, and this is what we offer in MLI as well. This is sort of going over, how this concept would work. So, if I have a variable xj and set that to one constant value, then I score the model, and then I get the average and the standard deviation. I can plot those and see how the outcome changes based off of setting that xj to certain values. So this is, like I mentioned earlier, this is sort of some examples. The PDP can be flat. That should indicate that not much is changing with the model outcome as I vary the feature itself. So maybe this is something you should look at from a local scale. You can also look at the PDP, like the bottom one there, where it's sort of a spike and then it levels off a lot. So all of this is basically going over the behavior of the model from a global scale, and based off of your domain expertise or what you know about the data set, you can verify if this makes sense or not. So the next step is looking at local feature importance. So MLI, we have this dashboard where we have something like a K-line plot, feature importance. We have PDP, and we have the decision tree surrogate model. This is all shown at a global scale initially, but you can zoom into, like, let's say, a row, and you can see the reason code for that row, the feature importance for that row, what path it went down in the decision tree surrogate model, and sort of this concept of ICE, which is the same as PDP, but just done for a single row of data. So in this case, you see, highlighted here are sort of reason codes for the K-line plot on the top left there. This helps with, sort of debugging and drilling down from a global to local scope. So the The surrogate method used here is K-line, which I will go over in later slides as well. So there's this concept of line, which is used for getting local reason codes. The idea here is that I have some row of data, and then I sample around that row of data to build out to sort of build out similar rows, and then I build a GLM to those rows and get reason codes for it. This is something that's been shown in literature with the line package. However, it can take a lot of time to sort of build out to sort of do the sampling approach. So here you can see there's the row which is indicated by the plus sign. I sample around that row to build out a data set, then I build a GLM, and then I get reason codes for that row. What we do with the MLI module is we do this concept called K-line. So instead of sampling around specific rows, what we do is we build, first do K-means to cluster the data, and then for each cluster, we build a generalized linear model, which can be used to get reason codes for rows that fall within that cluster. So this is sort of a much faster approach than sampling, which can take quite some time. And then based off of selecting a row in the K-line plot, which shows here, we selected a row, it belongs to cluster 2. We can see where the feature importance for that row. We can see its ICE plot on the bottom right there, so comparing that to the PDP plot, and we can see what pathing went down in the decision tree model itself. So once again, this helps with drilling down to what's happening for specific rows, and also helps with debugging as well. Another thing we offer with K-line is these reason codes that you can get for a specific row. So once back here, you can see the explanations button. I can click on that explanations button and then get English written reason codes to understand why a certain prediction was made for the model itself. And this is going over how you can look at, in the decision tree surrogate model, what path this row went down to sort of understand the reasoning behind the prediction itself from a local perspective. And then we also offer local feature importances for random forest, for the random forest surrogate model, and for the Leland covariate out, we offer it for Shapley as well. One thing to keep in mind that I mentioned earlier is with local feature importance, you can get this concept of adverse action notices. So what an adverse action notice is a set of reasons to explain why a lender or employer has taken some negative action on someone. If machine learning is used to sort of make these decisions, then generating these adverse action notices are very important. So in the data set we're using, it's the credit card data set, and we're predicting if a person will default on their net payment or not. In this case, we sort of want to understand why a certain reason was made, just in case someone asks, why they were denied. We need to have some solid reasoning behind why a decision was made. And if we're using machine learning models and we're doing it in an automated fashion, we have to make sure that those reason codes make sense. So this is something we offer through the MLI module itself with various methods like local feature importance, Shapley values, K-line reason codes, and various surrogate models you can look at as well. Using all this information together, you can sort of figure out why certain decisions were made, and then based off that, you can debug and see if it makes sense or not. And this is sort of going over, this is sort of just like a plot of Shapley values for a local row, and you can see here what's important and what's not important as well for this specific row compared to the global case. Another thing we offer is this concept of ICE. So ICE is individual conditional expectation. The concept here is running PDP for a specific row. So you can look at everything on a single plot. So those yellow dots there is the global PDP. The gray plot is for a specific row, and that dashed line is the model prediction itself. So based off this, you can look at the distribution of the model outcome. On average, you can look at the distribution for the specific row and then compare that to what the actual score was. We also offer in Driverless AI auto documentation. So this is a way of seeing what the model or how the experiment played out in Driverless AI, seeing PDPs again, in this case, you can look at out-of-range PDP. So, how is the model behaving when it sees data that it did not see in training? So this goes into the sensitivity of the model itself. So once you have this auto documentation, this is something you can go over. Is the human review aspect that comes into play. The MLI module itself also offers the ability to download all the images, so these can be shared amongst team members or other people in your company or organization. And this is a good way to get feedback from your experiment. And since Driverless AI is an automated system, you can do this with various experiments and share the results with pertinent people. This is sort of going over the model documentation again. And one thing we're offering in the next release of Driverless AI is a disparate impact analysis. So this is a way to look at various metrics across groups to see if there's any disparate impact. And by disparate impact means there's unfair treatment of certain protected groups. For example, if you build a model that was predicting defaulting on loan, and in the model itself you did not use, let's say, the gender variable, that's not to say that disparate impact has been completely avoided. There could be a fair or an unfair treatment between males and females. So you can look at that with the disparate impact tool in the MLI module itself. The last thing we offer is width and sensitivity analysis. So this is a sort of a validation technique. The idea here is basically you want to take the inputs and change them and then see how the outputs are changing. This is a very good way to model debugging, a very good way to figure out if there's any interesting behavior going on with the model itself and addressing that behavior before it's deployed. And this is sort of this new concept we will have in the next release of Driverless AI in the MLI module. With that, I can open the floor for questions.
All right, thanks, Navdeep. As these questions start rolling in, just want to remind everybody that we offer a 21-day free trial of Driverless AI. You can access that from our website. I will provide a link in the attachments post-webinar as well, but the website is h2o.ai/try. That's a quick way to get to the sign-up page to request a free trial license. And it's a great way to just get your hands-on an automatic machine learning platform and start playing around with MLI as it pertains to your business use case.
I can sort of jump right into Driverless AI. So like Patrick mentioned, you can get your hands on a 21-day trial. I'll just quickly go over some of the concepts from the presentation and show you in the software itself. So in this case, I've sort of uploaded a data set, which you can get from your file system, S3, Hadoop, URL, or you can just upload it directly from your own computer if you have Driverless AI running on an instance or anything like that. In this case, I uploaded the two data sets, the credit card data set that I mentioned in the PowerPoint. There's a train set and a test set. And one thing you can do with Driverless AI is you can click on the data set and sort of look at the details. So this is sort of going over the distribution and the breakdown for categorical variables, the breakdown for continuous variables. You get many characteristics like the count, number missing, mean, median, mode. So this is something that goes into the initial aspects of EDA itself. Once you've done that, you can sort of visualize data set. I've already ran this, but initially you would just click on data set and then click on visualize. So here you can go to AutoViz, you can look at the training data set. And these are all the visualizations that have been made, and these are automated insights that are made from the AutoViz module itself. So we can look at things like correlation plots. In this case, the bill amount to bill amount to. You can look at the help section, which sort of gives you an English explanation of what you're seeing, and you can download the plot itself. So this is sort of available, or this is available for all data sets that are imported, and this is sort of a very good initial step in a data science pipeline. I mentioned before that once you've done AutoViz, you can sort of go into an experiment. So what I was mentioning earlier is you can click on the data set you want to use. one key aspect is you don't want to use, protected groups in your experiment itself to avoid any bias. This is not to say it will completely avoid bias, but this is a good first step. In this case, we're trying to predict if the person will default next month on their credit card payment. So I was mentioning earlier that you can go into the expert settings for the experiment itself. You can select which models to use. So here I can, I can just turn on, use attributes, but turn off everything else, for example. And then I can say here, the ensemble level, if I set that to 0, that means a single model will be built. If I go to the recipe section in the expert settings, I can select which transformers to use or not to use. So this goes into, controlling or constraining the type of feature engineering that's done in your pipeline. You can also select the models here, but I've already done that in the previous pane. And, there's many other things you can enable or disable in the experiment itself. Once that's done, you can see a sort of summary of what's going to happen with this experiment. The main thing to consider for this talk is, the monotonicity is constrained, and feature engineering is sort of not as complex as one can make by setting this interpretability knob. Another thing you can do that I mentioned is you can build this compliant mode. So this is the pipeline building recipe. So it's normally auto, but you can set the compliant, which would basically only build GLMs or a rule fit model and nothing else, and it'll constrain the types of features that are made and sort of control the interactions used to avoid anything too complex. I've already sort of built these experiments previously, so this is sort of the compliant experiment itself. So you can see that the features engineered are pretty straightforward. So this is out of fold mean of the response, grouped by whatever folds are used. So this is all like group bys or the original feature itself. Nothing too complex has happened here. Once this is done, you can see things like the ROC curve, lift, gain, the KS chart, summary. You can go on to diagnose this model on a different data set. So here I've diagnosed it on the test set that I passed in. So just so people want to understand how that works, you can just go to Diagnostics, diagnose the model, select which experiment you want to use, and then select the data set you want to diagnose it on. Once that's done, you just launch it. So here, we've done that, and the beauty of the AutoML system, the beauty of Driverless AI is I can do this for many models, and I can compare and contrast, and I can share results with many people. And based off of that, I can iterate a lot faster. So you can take this approach of responsible ML with an automated system and do it for many use cases or try many approaches to your problem, in a fraction of the time that a normal user might take without an automated solution. Once we've done the diagnosis, we can go back to the experiment itself, and we can, quick interpret this model. And these are the panes I was talking about before. We sort of get a summary of what happened with the experiment itself. You can look at the feature importance of the model in the original space or the transform space. You can look at the Shapley of the model itself, partial dependence. This is the disparate impact. So like here, for example, in this model, we didn't use the gender variable, but we can still look at it from a disparate impact testing standpoint. And we can compare everything, let's say, to females. So we're comparing males to females here, and we can look at things like the accuracy, is it significantly different in precision, all these type of things. In this case, what disparate impact uses is the 4/5 rule. So basically, if any one of these metrics is greater than 1.25 or less than 0.8, then they'll be flagged as having disparate impact. This is a really good tool to sort of explore and see if there's any unfair treatment going on. We also have sensitivity analysis here. So for example, what I did for this experiment specifically is I looked at residuals of all females that had a false positive, so they were falsely predicted as defaulting next month when in reality they did not. And the main focus I wanted to look at is the ones that barely miscut. So here we see the cutoff is 0.2349. These are observations that barely miscut, and we want to explore and see, could we have prevented this somehow, or does this make sense? And this is something you can get with the sensitivity analysis application. And then you can sort of zoom into, the K-line plot, the decision tree plot that I showed. This is a random forest surrogate model, so you can get feature importance and local for all these, and then you can look at a dashboard itself.
Great. So we do have a couple questions here. The first is, does H2O have an option to build a model with streaming data?
From Driverless AI, no.
Okay. Next, is model interpretability and explanation only available in H2O Driverless AI?
So the MLI module itself is sort of built for the Driverless AI application. In Driverless AI, of course, people can still see my screen. You can do this concept of new interpretation, and you can upload a data set with predictions, for example. So this is bringing an external model per se, because it's a data set with predictions from some external model, and you can run that without a Driverless AI model. And then you can sort of get, maybe what you would get from that point is the surrogate models. You would get reason codes for your external model itself. Another answer to that question is a lot of the methodology that I went over, like PDP and ICE and Shapley, is available in open source H2O3 as well. However, those are available through a Python or R interface, so it doesn't really come with the graphical user interface, and K-line and all those things are not available in H2O3.
Great. Okay, I think we have enough time for one more. So once a model explains its decision and unintentional discrimination is found, what are the next steps to actually retrain the model to remove these discriminations?
So the next step is you can avoid this type of thing by using a lot of the open source libraries that are out there. So there are some things like AI 360 that can sort of de-bias the model itself. We are working on getting this into Driverless AI through our own means. So that's what you can sort of do at this point, under my opinion. That's what you can do at this point. Like I said, it's usually not enough to just not use a demographic type of variable. You have to consider correlations with that variable itself, which you might have latent variables that are used as well to sort of pick up this discriminatory behavior.
Okay, let's just try to do one more here. Upon loading the data, one could choose a target column. How could one change the integer column to categorical?
I think that is built into the next release, but I can't see how it's done today. Yeah, that's something I think I would have to answer at another time.
Okay, no problem. So to wrap up, I just want to say thank you to Navdeep for taking the time today and doing a great presentation. I'd like to say thank you to everyone who joined us as well. The presentation slides and recording will be made available through our Bright Talk channel, and have a great rest of your day.